Hello, my dear students, and welcome back to our concluding coverage of Chapter 2. I want to talk to you about formulas and molecules. I backed up a little bit in our talk to uh, remind you that we talked about atoms and Dalton's atomic theory. And then we talked about elements and a little bit about the periodic table. And now we want to build on that by building these elements up into compounds, chemical compounds. And we write chemical formulas and automatically assume you've seen them. We did this in the last section without, they do it in the book without stopping to say, hey, look, when I say O2, that means two atoms of oxygen put together. When I say H2O2, hydrogen peroxide, that means two atoms of oxygen put together with two atoms of hydrogen. And this is termed a chemical formula. Okay? So, we have chemical formulas. An empirical formula isn't, it's useful for chemical determinations and classically determining the formulation or what atoms were present in what ratios in a substance. These days, we know so much about so many chemicals that it probably isn't as useful outside of quantitative chemistry and gravimetric chemistry uh, for understanding chemistry. But that hydrogen peroxide, H2O2, the stuff in the brown bottle that you get that bubbles up when you put it on a cut, you shouldn't put it on a cut. It doesn't do any good. You just need to use soap and water. But it has a formula of H2O2. That's its molecular formula or its chemical formula, okay? But if you go back to Dalton and you talk about the simplest whole number ratio, if I divide both those by 2, I get HO. That's an empirical formula. Okay? That's one of these. And sometimes that's all you can determine until you have it about the chemical makeup of a substance until you have additional information. So if you know the molecular formula of a compound like H2O2, you can determine the empirical formula, but the reverse may not always be true. This was really important when people were doing, for example, formulas and chemical compositions of sugars and different sugars. So let's talk about different formulas. A chemical formula, a molecular formula, tells you the number and type of each atom present, but they don't tell you how they're attached. For example, CH4 is the formula for methane. There is something called a structural formula which tells you how they're attached. A carbon in the middle with 4 hydrogens attached to it, surrounding it. And yet that's not very accurate. It's a flat, planar arrangement of atoms, and they don't exist in a flat, planar form. They have a three-dimensional shape. In this case, methane takes the shape of a tetrahedron, a regular 4-sided figure, okay? A little pyramid, not an Egyptian pyramid with 4 sides and a square base, but a regular triangular tetrahedron with 3 sides and another triangle, identical triangle on the base. That is somewhat depicted in a perspective drawing if you know the rules for the drawing. A dashed wedge and an angled wedge They can project out of and into the board if you're drawing on a board or on the paper. They give you some perspective if you know how to read them. The ball and stick model gives you kind of an idea, and they're easy to work with, and yet I promise you that electrons don't spin around one of these atoms, go through this little tube, spin around this atom, and then travel back to the little tube. In forming these bonds, they create bonding orbitals that are clouds of electron that fill up the space, something like this. And space filling models are the most accurate model there is. And with experience, you can go from a chemical formula and be able to visualize what that molecule looks like in space, because there's some pretty standard algorithms, some standard ways that molecules come together that we can deduce from their chemical structure. So, first thing is, a while back we said we can't agree completely with John Dalton. We have to modify his model of the atom, or refine, I think would be a better word, his model of the atom, to say that not all atoms of a given element are identical. We have isotopes. But we can also have different forms of an atom. If they gain or lose electrons so that the electrons and protons are no longer balanced, you don't have a balanced charge, but they acquire a charge, either a positive or a negative charge. And a charged form of an atom is termed an ion. And it's formed when an atom gains or loses electrons. If you gain an electron, you form an anion, a negatively charged ion. And you can gain more than one. If you gain one, you get a -1 charge. If you gain two, you get a -2 charge. If you gain three, you get a -3 charge. And if you lose an electron, remember, those electrons are negatively charged. When you lose something negative, you become more positive, and you become a cation. I had a teacher tell me once, see the little plus? That's how you remember cations are positive, and anions have an N for negative. Of course, so do cations, but however you want to remember it. But cations have a positive charge. If you lose a single electron, you will get a +1 charge. And if you lose 2 electrons, you will get a 2+ charge. And we write the charges, not the way I've written here, okay? It's just a minus if you lose 1. We don't write -2 anymore because someone might interpret that as a mathematical function, I guess. So we write 2 minus, and we write 3 minus. Similarly, we write plus. The 1 is understood. 2 plus, 3 plus for the aluminum ion. And they're written as superscripts. So if I write Na for sodium, named after the Latin natrium, the Latin term for sodium, I write sodium with a superscript plus. Again, the 1 is understood. And I know that now I have a charged species of sodium with a +1 charge. Okay, so let's talk about some of these ions. The cations, if you look, metals tend to form cations. Metals have some of their properties We haven't talked about metallic bonding yet, but they're viewed as nuclei floating in a sea of electrons. When we talk about how metals are bonded to each other to form a large chunk of metal with a lot of atoms in it, and they have an excess of electrons. It explains their properties as good conductors of electrons, and it also explains their propensity to lose electrons. They've got plenty of electrons, they don't mind losing one, and so they tend to gain positive charges as they lose those negative charges, and they tend to form cations. So, and we call them the ion. There's another name for the hydrogen ion called the proton, hydrogen ion or hydrogen cation, lithium ion, sodium, potassium, cesium, silver, um, +2 ions, zinc, cadmium, copper. Uh, Copper can also be +1. These transition metals have multiple charges. Some are consistent. I'll tell you what the consistent ones are. Now, we do not use the term cuprous. We call it copper 1. The Roman numeral 1 in parentheses denotes the fact that it has a +1 charge. Copper 2 has a +2 charge. So some metals, especially the transition metals, tend to have multiple ionic forms, okay, in here. Some of the others over here, lead and mercury, for example, lead for sure, I want to say, uh, have multiple forms as well. But the transition metals have multiple ionic forms, and we denote the charge with a Roman numeral to distinguish them. We used to use terms like ferrous and ferric for our iron 2 and iron 3 ions, respectively. But now we say iron 2 and iron 3. And it's so handy. I love it because you don't have to learn all of these Latin terms for these ions. You just say nickel 2 or nickel 1. So you can name them and know their charges by the Roman numeral attached to them, which you pronounce when you talk about a copper 1 cation. Okay? We'll practice doing this, and you'll get some practice doing it, and you'll see. I will also say, when you take a test, you will have a copy of the periodic table, and we'll talk about that later when we're doing our assignments, and you'll have a list of common ions. The anions, and there was one I left off before, are the negative ones. If you look back, you'll see that the group 7 halogens always form a -1 ion. And, or for our purposes, always form a -1 ion. Fluorine, chlorine, bromine, iodine. Those anions are formed by gaining an electron, and we change the ending to "ide." Okay? So hydrogen can also form a -1 as well as a +1. So it's termed the hydride. Fluoride, chloride, bromide, iodide. Oxygen, sulfur form -2 ions, oxide and sulfide. Peroxide is an O2 with a 2-. Nitride is a 3-. We'll explain why those charges are preferred when we get to them. And then you'll notice we have a new class of ions. Not new because I didn't mention one. Occasionally, we have some compounds, not some compounds, but some ions that are made up of many ions called polyatomic ions. In the positive realm, There's ammonium ion. Okay. It's formed by ammonia gas combining with water to form ammonium ions plus hydroxide ion, ammonium hydroxide. And this OH minus hydroxide ion is a -1 polyatomic ion too. Some of the other common ones are listed here. Acetate, the anion for acetic acid. Chlorate, you've perhaps heard of nitrate, sulfate, phosphate. You may have heard of them in the context of fertilizers or different compounds. Those are polyatomic ions too. We'll give you a list of them and make sure that you have some experience using them and naming them. So, if you have sodium forming a +1 ion, it loses an electron, and you have chlorine forming a -1 by picking up that electron, or, electron from somewhere. What you end up with is what we write as Na plus and Cl minus. But here you have opposites, and you know what opposites do. They attract, and they come together to form a complex, and this is the structure of salt. They pack in together. You probably would never, we write it as NaCl, sodium chloride, and we name it sodium chloride. Remember the chlorine -1, the anions, when we form them from elements, we change the ending to "ide." The sodium chloride compound, you probably would never have a single sodium and a single chlorine together, because when they come together, they pack together in a specific geometry, and they coordinate with each other, following established patterns that tend to be really regular and constant, so they tend to crystallize. They have very high melting points and are formed from oppositely charged ions and tend to dissolve in water and can then conduct electricity. Pure water does not conduct electricity. And one of the problems people have is writing formulas for ionic compounds. The charge on the overall compound. Sodium has a plus charge, chlorine has a minus charge. They have to come together to form a neutral species. +1 -1 equals 0. If I have magnesium and I want to form, which forms a 2+ ion, and I have chloride, which forms a 1- ion, I'm going to form a compound, magnesium chloride, but I'm going to need 2 of these to neutralize 1 of these, so I'm going to have Mg, the one is understood, Cl2, magnesium chloride. Very common laboratory salt that is itself neutral. And the biggest problem some students have is if you take a compound like magnesium ions, Mg2+, and nitrite ions, which are 3-, how do you mix a 2 and a 3? Well, they have to balance, and some people call this method also crisscross. But obviously you take 3 magnesiums to get to +6, and you take 2 nitrites to get to -6, and you end up with a formula of Mg3N2. This is a complex way to do it, in the sense that it is taking out And this um, uh, way of putting them together does work. The charge on the cation becomes a subscript on the anion, the charge on the anion becomes a subscript on the cation. So if you can remember that, make sure that you do it that way. And if it is not the lowest whole number ratio, divide by the greatest common factor to get there. And that seems kind of difficult. Just remember the charges have to add up to zero. You have to have a neutral species when you make the complete ionic compound. It must be net charge of zero, even though the ions themselves will have their charges attached to them. You can separate these again by heating to very high temperature. When they're molten, they separate, and when they're dissolved in water, they separate. So, the way we name them, we write the cation first. If it has more than one possible charge, think transition metal, use a Roman numeral. I'll give you a list. If an anion is an element, you change its ending to "ide," phosphide, sulfide, nitride, oxide, chloride, and then write the name of your ion. In this case, it was magnesium nitride, and in the case I gave you down here, it was magnesium chloride. Okay? Now, those polyatomic ions get complex. Many of them have oxygen in them. They're called oxyanions, and I will say the one with the most oxygens, not the one with more oxygens, the one with the most oxygens ends in 8. Sulfate is SO4. If you have one fewer oxygen, it ends in ite. So sulfite is SO3. Nitrate, ammonium nitrate, common fertilizer, also an oxidizer. Ammonium nitrate, NO3, and nitrite is NO2. And they have the same charge, but one less oxygen from 8 to ite. Now, what if you have just SO2, 2 minus? What if you lose another oxygen? Then we go under, and we call it hypo, as in hypodermic needle goes under the skin, or hypoglycemic diabetic has low blood sugar. It's called hyposulfite. Okay? And that happens sometimes, okay? If you discover a form that has even more oxygens, it is called, you add the per to it, okay? So, I don't want to cover too many of them, but as you go through the groups, forming these oxyanions with group 4 carbonates, group 5 nitrates and phosphates, group 6 sulfates, and group 7 chlorates, among other things, bromates and the like, you can kind of tell the difference between how many oxygens you'll have and how it changes. But the one with the most oxygens tends to end in 8. That was how they named them. And then they discovered other forms that had more. Not all of them have a form with more, but then we add per. For example, chlorate is the best example because we've discovered everything in both directions. Chlorate, ClO3, the 8, has 3 oxygens. The ite has 2. The hypochlorite, as in sodium hypochlorite or bleach, has the hypochlorite with the hypo attached. And then, sure enough, they discovered a form with more in it, and that's the per with the 8 on the end, chlorate. Okay? This one would be ite at the end with the chlor in the middle. So, those terms, when you see them, just remember they have some logic attached to them that, with sufficient experience, practice, and a little review of the rules of nomenclature, will give you an idea of what those compounds are when people name them. Now, you may have heard some of these things like nitric acid or hydrochloric acid. If it's a single element, chlorine, bromine, or iodine, changed to the chloride, bromide, and iodide combined with hydrogen, this becomes a hydrogen donor, which is what we term an acid in one of our 3 definitions of acids. Okay? Lewis base acids, Arrhenius acids, etc. And the hydrochloric, hydrobromic, hydroiodic are very common acids. If we, for example, have sulfate with hydrogen, and sulfate is a 2 minus 1, when we combine it with 2 H pluses, because we need 2 to balance it, we will make this acid H2SO4, which we call sulfuric acid. So we change sulfate to sulfuric. And the ic acid arises from the 8 salts. So chloric acid came from chlorate, perchloric acid came from perchlorate, and nitric acid came from nitrate. If I start with nitrite, if I start with the ite salt, I end up with the us acid. So I know these relationships because I've been doing this for 40 years. But in time, hopefully you'll learn and get some of this nomenclature. Now, if we are dealing with molecular compounds, these are compounds that are formed with covalent bonds, not from ions, and frequently with the nonmetals. Okay? Then, for example, water. Now, it has a trivial name, water. But its formal name is, we use Greek prefixes or prefaces, however you want to say it, to denote the number. And this could be dihydrogen monoxide. But we don't usually use the mono unless we need to totally distinguish something from something else. And we do not use it on the first element. Okay? So, for example, carbon monoxide, we would not say monocarbon monoxide. And many compounds, common chemical substances, have trivial names that are accepted. And you would maybe be correct saying dihydrogen monoxide for your water, but people would look at you funny. People who know the rules would know what you're talking about, but everyone calls it water. And there are a few other compounds like that. Carbon monoxide could be carbon oxide, but carbon dioxide is clearly CO2. Okay? And, we'll talk about some other ones, phosphorus, pentachloride, and the like. So, the ending on the second element is changed to "ide." Carbon tetrachloride means 4 chlorides. Carbon dioxide, as we said, name 2. Here's a common one, dinitrogen pentoxide. Okay. And if you have, for example, a prefix ending with A or O, penta, mono, and the new element begins with a vowel, you combine them. So we don't say pentaoxide, we say pentoxide. Just the way it works. If you said pentaoxide, no one would say anything. Now, organic compounds, my specialty, because I am a biochemist, have a complete system of nomenclature that occupies a significant portion of your course in the second year of chemistry and the study of organic chemistry. Organic chemistry is a study of compounds containing carbon. And it has a unique system of nomenclature that there's no point in covering because it would take a lot to do. Again, you use the Greek prefaces, but the different endings mean many different things. For example, an ane is a simple hydrocarbon compound made up only of carbon and hydrogen, and they're a family of compounds with increasing numbers of carbons. 1, 1, 2, 1, 2, 3, 4. And you start out meth for 1, eth for 2, prop for 3, and after that you use your Greek numbers. Bute, pent, butane, pentane, hexane, heptane, octane. You may have heard that with gasoline. Nonane, decane, undecane. It goes on up to hundreds and more of carbon atoms. So, and then you have to add on the names of functional groups. Typical one is an OH, which typically ends in all. It's an alcoholic OH. Although this could also be a hydroxy group, depending on its position and its what compound we're talking about. So it gets extremely complex. Let's forget about the naming of organic compounds for now and hold that for organic chemistry. That's it for this last section in Chapter 2. I'll get Chapter 3 posted in a couple of days, but I will give you a week or more to do all the assignments. Remember, the course is asynchronous in the sense that you will be working at your own pace, but I want to get those assignment dates. I'd like you to pay attention to them. I will enforce them, though perhaps not entirely rigorously, when I have received messages from you about why you might need an exemption. But we will get Chapter 2 up, the assignments all up and assigned. Then I'll put the Chapter 3 and Chapter 3 assignments up, but I won't put a very early assignment date on them because I want you to, of course, go in order and do these things. And as I make the assignments, I will also be posting in the beginning some discussion about how you answer them. And later, I'll leave you more on your own, but try to work the occasional sample problem where you see how things are worked out, and then you substitute in the values or the elements or the compounds for your particular problem. So until we meet again on this platform, please take care and stay safe. Goodbye now.